Today we are talking about the relationship between differentiability and continuity of functions. So we're just going to start with the theorem that gives us that relationship. Differentiability implies continuity. What does that mean basically? Once you know that a function is differentiable, you can take the derivative of it everywhere. That means the function is continuous everywhere. So if we write that in math terms, if f is differentiable at x equals c at a point, then f is also continuous at x equals c at that same point. And does that make sense? I mean, it should make sense. I hope that it makes sense. So yes, I think that it makes sense. Now, why does it make sense? Well, if I can take the derivative, then all of the three-part definition must be true for continuity. The function has to exist, first of all. If there is a hole or an asymptote, I can't take the derivative there. The limit as x approaches c of the function must also exist. It must be going to a single place from the left and from the right, and that function has to be equal to that limit, because we know that if we have a hole, for example, then we cannot find a derivative at a hole, which means we would not be continuous. Does that mean that if a function is continuous, then it's automatically differentiable? So let's take a look at a function that I have randomly selected. Okay, so f of x is equal to absolute value of x. So let's start with the first question. Is f of x continuous at x equals 0? So we're going to use our three-part definition to determine if f of x is continuous at x equals 0. So first and foremost, I need to find f of 0, which would be the absolute value of 0, and 0 has no sign, so it doesn't matter whether it's positive or negative, so that's 0. Then let's look at the limit. The limit as x approaches 0, let's say from the left of absolute value of x, is 0. The limit as x approaches 0 from the right of absolute value of x is also 0, which means the limit is 0. Which means the function value is equal to the limit value. So f of 0 is equal to the limit value, which means f of x is continuous at x equals 0. Now, just quickly, I'd like to think about what this graph looks like. So I'm just going to give myself a real quick sketch right here. And the absolute value of x is just your V shape. And yes, that is continuous. I can draw it without lifting up my pencil. So let's move on to the definition of the derivative. So we have to use the definition of derivative now in the next part to determine if we can find the expression for f prime of 0. Okay, so we're going to find f prime of 0. We're going to use the definition of derivative, and I'm going to use the c definition of derivative. So I'm going to have the limit as x approaches the c value, which is 0, of f of x minus f of the c value, which is 0, all over x minus 0. Again, that's the limit definition of derivative at a point x equals c. So now I'm just going to plug in what I have. So in this case, my function is the absolute value of x. So this will be the absolute value of x minus the absolute value of 0, which we've already found to be 0, all over x minus 0, which is just x. So if I simplify that, just so it doesn't look quite so complex, I'm going to get rid of that 0 on the top. And so I have absolute value of x over x. And again, this is my derivative at 0. So my derivative at 0 is the limit, as x approaches 0, of the absolute value of x over x. Well, we really need to evaluate this limit from each side. So I'm going to start by looking at the limit as x approaches 0 from the left of the absolute value of x over x. So when I am to the left of 0, let's say I'm using x is -1. When I plug in a -1 on the top, I take the absolute value of it and I get a positive value. And when I plug in a -1 on the denominator, I get a negative value. So if I were to just use 1 to plug in, I would have -1 over -1, absolute value of -1 over -1, which ends up being 1 over -1, which ends up being -1. And that will work for any negative x value. In fact, I'm going to rewrite that. You can leave that as is. I'm going to rewrite it though with x's. So what I really have, if I take a negative x value and I divide by a negative x value, and this is saying that x is positive, by the way, then I have x being a positive value over negative x, which simplifies to simply a -1. So the limit as x approaches 0 from the left is actually going to be -1. So let's look what I get when I approach from the right. So the limit as x approaches 0 from the right of absolute value of x over x, same concept is going to hold. The absolute value of a positive number is still positive, and the denominator is still going to be positive, which means the top and bottom should simplify, and I should get a +1. So at this point, I need to stop and ask myself, what does this mean about the derivative? Well, what this means about this limit that I found over here is that it doesn't actually exist because the left-hand limit and the right-hand limit are approaching two different values. So if I wanted to rewrite this as a function, f prime of x, f prime of x is going to be equal to -1 whenever x is less than 0, and it's going to equal 1 whenever x is greater than 0. And at x equals 0, I can't actually find that derivative. So I need to determine now, is f of x differentiable at 0? And the answer to that is no. So f of x is not differentiable. Sorry, that didn't quite fit, is not differentiable at x is equal to 0. Now, at this point, if you're just blindly writing down what I'm doing, I need you to stop the video and go back and look at what I've done and make sure you understand it, okay? Do not simply write down whatever I've written down and say, voila, I watched the video lesson. No, we need to learn from this lesson. So please, at this point, if you're not getting it, stop for a minute, stop the video, look at the paper, and make sure that it makes sense, because this should make sense. So now I'm going to go ahead and sketch the graph of the derivative. And what the graph of the derivative is, well, I know it's negative. My derivative is -1 when I have values small, x values smaller than 0, and I'm at +1 when I have x values larger than 0. So my derivative is actually going to look like this. I should probably label that as f prime of x. So, question at the bottom. If a function is continuous, is it differentiable? So, in this one that we just did, we had the graph of the absolute value of x, which looks like this. This is continuous. However, it's not differentiable at x equals 0. And we can see the derivative is right above. And the reason, if I look at the function, it's not differentiable is because I have what's called a cusp. Right here, we used to call that a corner or a vertex or something along those lines. We had polynomials. In graphing, we actually call that a cusp, where we have a sharp change in direction. The key to the cusp is the slope on the left side will be one sign. The slope on the right side of the cusp will be a different sign, at which point it's not differentiable. So it's not differentiable at a cusp. The cusp will be continuous in the function, but not differentiable for when we find our derivative. Okay, so let's move on. We're going to do this problem. Let's get down into our mathematics, and what we're going to do is find values of a and b that make f of x differentiable for all real numbers. Okay, so once I start with the fact that something is differentiable, I automatically know it must also be continuous. And I need that information. Right now I have a piecewise function, and in order to be continuous, I need those two pieces to connect. In order for it also to be differentiable, I need the two pieces of the derivative to connect. So the first thing I'm actually going to do is actually write the equation for the derivative of this piecewise function. So when I do that, I'm going to take the derivative, remembering that a is a constant. It's just a number. So when I take the derivative of ax squared, I'm going to use my power rule, and I end up with 2ax. That should be the derivative whenever x is greater than or equal to 3. I'm going to do the same thing with the other piece of the function, remembering that b is just a constant. So when I take the derivative of bx minus 2, I simply get b. The derivative of 2 is 0. And that is good when x is greater than 3. Oh, sorry, that's a mistake in my handout. This should be less than, and this should be less than here as well. I apologize, I did not catch that. Okay, so here we have our derivative. Again, I apologize for the mistake. So at this point, I need two things. I need the two pieces of the derivative to connect. And we need to connect at the x value that separates them, which is at x equals 3. And so in doing that, I need 2ax to be equal to b at x is equal to 3. So that's 2a times 3 is equal to b, which gives me 6a is equal to b. Now at this point, I cannot actually find a, and I cannot actually find b. So now I need the other piece, which is our continuous piece. So I need the two pieces of the function. They also have to connect. And these must connect at, again, x equals 3. So from that, I'm going to have 2a, excuse me, I'm using my function, not my derivative. I'm going to have ax squared is equal to bx minus 2, and that has to happen at x is equal to 3. So I'm going to have a times 3 squared is equal to b times x, which is 3 minus 2. So that leaves me with 9a equals 3b minus 2. At which point I have two equations with two unknowns, and back a long time ago in Algebra 1, when you learned that, you thought, why am I ever going to have to use that? Well, here we go. Here's a perfect instance of where we have to know how to solve a system of equations. I'm going to go ahead and use substitution. This one's laid out pretty well because it's telling me what b is. B is 6a. So I'm going to take my 6a and I'm going to plug it in for b over here. When I do that, I have 9a is equal to 3 times 6a minus 2. And that I can now solve for a. I'm going to scooch down just a little bit. So I have 9a is equal to 18a minus 2. And that gives me negative 9a is equal to negative 2, and a is 2 over 9. I got a fraction. Is that okay? Yes, yes, we're in calculus now. We can get fractional answers and decimal answers, and it's okay. So now I'm going to take this, and I'm going to plug it in over here so I can find b. So now I have 6 times 2/9, and that is going to be equal to b, which is 12 over 9, or in other words, that is 4 over 3. So now we have our b, now we have our a. If you so chose, you could now graph your function with this a value and b value plugged in to make sure that my function is is continuous and differentiable. And you're welcome to do so. So please make sure you understood everything in this packet, but bring any questions that you have to class and have a nice evening.